Hello, this is Christopher Cole with CS6263. I will be doing a paper on differentially private password frequency lists. Or in other words, how to release statistics from 70 million passwords on purpose. This was written by Jeremy Blokey from Microsoft, Anupam Datta from CMU, and Joseph Bonneau from Stanford. This presentation will go through how administrators need to be able to secure data and passwords effectively through various methods. One such method being collaborating with differentially private password frequency lists, how adversaries acquire passwords, and the problems that can arise from that. We will also learn about the RockU data breach and how Yahoo has collaborated on this effort, displaying how it is possible to use user data and passwords without revealing private information or other data that could compromise such information. We will then conclude the presentation with how this can impact the industry and prevent future data breaches through collaboration. This presentation takes on the perspectives of administrators and adversaries. For the remainder of this presentation, we will define administrators as a person who has the responsibility of protecting user private data as well as proactively preventing that data from being breached. Contrarily, we will define an adversary as someone who is actively trying to acquire private user data via cracking their password. We will start by talking about administrators and how they can effectively use password frequency lists, how they need privacy guarantees, how they select password composition and strength determination of passwords, what some of their security concerns might be, and the necessity for perturbed lists and partitions. We will then move to adversaries and some of the measures they use to try and crack passwords. Primarily, be guesswork and how it is impacted by case strikes and marginal guessing cost. First, a password frequency list is a list of passwords by frequency. In other words, a password frequency list is a list that compiles how many users use the exact same password. That's what we mean by frequency. We will go into more detail about how lists can be partitioned and perturbed in order to obfuscate and organize the data in a later slide. Why do we want to know about a password frequency list or the information that it provides? Well, there are a number of reasons. For security purposes, a password frequency list can tell us how many users are using the same password. This can give security admin the ability to create measures that will make it harder for adversaries to be able to hack passwords, as well as implement measures that are less restrictive on users. In research, using a password frequency list that is not disclosing user data allows for a more open environment, which will allow for more testing and research of password encryption and protection and cryptography. Obviously, when it comes to password research and user private data, there is a need for privacy guarantees. There are a number of different ways to guarantee privacy. K-anonymity, for instance, simplifies data set to a generalized user. Take, for example, some user data in your email. Perhaps you have your first name and your last name and your age. Instead of providing your actual age, maybe 25 or 30, it would provide a range like greater than 20 and less than 30. This effectively obscures your data. Similarly, L diversity expands on K anonymity and ensures all classes have diversity. Differential privacy goes a step further and uses an algorithm to provide data, but not in a user-by-user way. Instead of providing individual data, it would provide data in sets. Instead of providing my age as an individual, it would provide a set of data with everyone who is within the age of 20 to 30. This prevents individual users from being individually identified. They are identified instead in a group set, providing more anonymity. This anonymity can be applied to a frequency password list and is called a perturbed list. It is a safety net for users in the sample data set in order to obscure data information of the user so that it is no longer usable by adversaries who would use that to perhaps glean information which would allow them to compromise their account. It thus makes it safe to release the distributed list. Besides requiring safety for our data to be used, we also have to have a way to use that data. A frequency list is partitioned by frequency of password use. A partitioned list is an ordered list of non-negative integers. It is useful to organize lists into partitions in order to see the frequency of which passwords are being used. For example, in the RockU incident, approximately 20 million users were using the same 2.5 million passwords, which turned into about 8 people sharing one password. This is obviously a serious problem. Since we're talking about passwords, here's some password information. Password composition or requirements typically include an uppercase letter, a lowercase letter, a special character, and a number, and possibly greater than a certain number of digits. Just saying all those requirements is a mouthful. It's no wonder these requirements typically frustrate users and cause them to select weaker passwords or forget their passwords more frequently. In addition, strength determination is often not include metrics for password usage, but measures a password independently of other passwords without using a frequency list. This can be a security concern when over 300,000 users might use the same password, such as 123456, which would give a potential adversary a very good chance of guessing their password. This is obviously a security concern, as can be seen in the RockU security breach, where 32 million passwords were stolen because they were left unencrypted in plain text in an SQL database that had at the time a 10-year-old vulnerability. This kind of security breach does not happen by accident, but happens through adversaries. Adversaries have a number of strategies that they use to try and guess passwords. In actuality, the feasibility of just randomly guessing a password is quite low. Unfortunately, adversaries typically have some kind of background knowledge on the users that they are trying to acquire the password of. This is why obfuscating information is incredibly important, so that when frequency lists are released, they do not give out more information of a user. Adversaries are typically seen trying to get a hold of user data. If there are n users in a data set, then there's a maximum of n passwords that an adversary needs to crack. Typically, they will have a hack budget of b guesses per user password. Once they have exceeded this budget, it is no longer feasible for them to try and continue hacking a password. For example, because they have locked the account. This is also called K-strikes, or the number of failed attempts you can make on a password login. With a good frequency password list, that is, a list with almost exclusively unique passwords, where very few users have the same password, you can increase the number of strikes you have because you can be confident that a hacker will not be able to guess based off of commonly used passwords. Alternatively, if your password frequency list is very similar, you would need to reduce the number of failed attempts before a lockout because the risk of finding the right password is higher. A distributed password list can help administrators see how many guesses a hacker would likely take before they would be able to find a password. This can give them the opportunity to plan ahead or put measures in place that will prevent that from happening. Measures such as key stretching, which allows an administrator to progressively extend the hash time for a password before submission based on the number of failed attempts. Now that we have explored how a password frequency list works, how it can be effectively administered by a local security department, and how it is effective in preventing security breaches, we will look into this solution. We will solve for how to develop an approximate differentially private algorithm that can allow the disbursement of frequency password lists. We will go through how it is important to implement differential privacy, some other information, how it is important to remain accurate, exponential mechanism, and approximate or relaxed differential privacy, and dynamic programming as part of this implementation. As we saw earlier, differential privacy is very important and provides safety so that one cannot derive any information about a user based on the released data of the research. Unlike in k-anonymity or L-diversity, differential privacy will obfuscate the data in a way that will not benefit an adversary if they were to get a hold of it. If the adversary already has background knowledge and is making educated attacks, a password frequency list will not help them make attacks using this method. Additionally, if a user has a weak password, the adversary, knowing the statistics of an obfuscated list, will also not be able to increase their probability or put the weak user at risk. Finally, the list will have a group privacy which prevents adversaries from discerning list changes, such as when end users are deleted or created. This further obfuscates the data and makes it harder for an adversary to use the data in an effective way. Unfortunately, differential privacy does degrade when lists are duplicated or there are similar passwords that are introduced into lists. While we do want to obfuscate the data in a way which prevents it from being reused or gleaned for more personal information, we also want to minimize the cumulative errors when making this differential privacy. We want to introduce password error, but not cumulative ones that will somehow change the data or increase the noise of our information. This is because we do not want to make the data some way inaccurate. In order to effectively retain differential privacy as well as the accuracy of the data, the algorithm selected for this solution will be an adaptation of the exponential mechanism algorithm. This is because it is well defined, even though it has an infinite range. It will preserve differential privacy, and it will introduce minimal cumulative distortion. Unfortunately, exponential mechanism is also exponentially time-consuming and would take too much time to be able to implement effectively on millions of users. Thus, the approach to take would be to relax it without compromising the privacy. This would be implemented by giving each partition a weight and completely ignore distributions that are very far from the real distribution. This would allow differential privacy for a very small value and provide minimal distortion. This method will be implemented through dynamic programming. This is because partitions will decompose well, which is good for dynamic programming, and it will enable us to use recursion, which is a very simple way to compute weights based off of previous partitions that have been computed. The implementation will be in two phases. First, in the pre-processing phase, an algorithm will compute all the weights and use special helper functions for the upper and lower bounding. Secondly, there will be a sampling phase where the algorithm will use an equation to sample from the restricted exponential mechanisms. Overall, this will give n time to the algorithm. Now that we have gone through how the solution will be implemented, we will look into the results of the data that was compiled, which we will compare with the actual data that was released. We will first look at the RockU data, comparing the results of a data frequency password list from the actual RockU breach data to those of the data created by this solution. We will then compare the data of a previously released password frequency list from the Banu research to a newly compiled list compiled by the solution algorithm. As we can see in the RockU data breach, 32.6 million users were affected by the data breach, but only 14 million passwords were revealed because so many of the users had similar passwords. In actuality, just a little over 1/3, or 11.9 million users, had unique passwords, whereas the other 20-something million users were sharing only 2.5 million passwords. This means of the 20 million shared users, there was about one password for every 8 people. The password 123456 was shared by over 300,000 people and was the most commonly used password. The analysis and obfuscation of this data resulted in extremely similar results to the original list. After the RockU implementation, which proved differential privacy of the data, Yahoo was willing to work with the researchers by contributing 70 million users to the research project. In order to implement this, a proxy was used in front of the live login to create a pseudo-random function. This function was then placed the data in multiple frequency lists before it was deleted. 52 different frequency lists were created during this research. No single user was a part of more than 23 of these lists. In all but 3 of the different demographic groups, the data was identical to the previously released statistics by Banu, which did not include data. These 3 small subset groups had larger margins of error, whereas as the data sets grew in size, the margin of error and entropy approached 0. The researchers concluded that this indeed is an efficient method for releasing perturbed passwords, that it guarantees minimal distortion and also guarantees approximate differential privacy on a scalable level with low distortion. Data comparison to actual data from Yahoo's 70 million users was near identical. Unfortunately, due to the nature of the collaboration, this data was not actually published, though in actuality the obfuscated data could be safely published. In conclusion, we can see that there is a need to prevent data breaches, that adversaries can and do attempt breaches all the time. It is important to prevent this, that password frequency lists can be helpful in analyzing various problems that adversaries will take advantage of, and that we can share these password frequency lists without revealing private data through differential privacy. But ultimately, we need industry buy-in to be able to have larger companies disclose this information so that researchers are able to analyze and improve upon it. Thank you for listening to my presentation. I hope you were able to learn something about differential privacy, password frequency lists, and how they can impact security in the world today. I hope that if you are in industry, you can help push this kind of collaboration at your company as well. Thank you and have a nice day.